For a few weeks, the skies have been holding their breath. On October 21st, during an event astronomers had flagged as a routine close passage, the object known as 3I/ATLAS, an interstellar wanderer that had been drawing attention since its discovery, did something no one expected. Under the brutal glare of the sun, it suddenly disintegrated in a violent, explosive breakup. The detonation hurled chunks of rock, ice, and dust into space, scattering a debris field broad and complex. Within hours, orbital analysts determined that a portion of that spray had adopted trajectories that intersect Earth's orbital plane. When NASA confirmed that debris from the explosion was on a path toward our planet, the global scientific community reacted with a mixture of excitement, urgency, and sober caution. From the moment 3I/ATLAS was first detected, it felt different. It arrived on a hyperbolic trajectory, meaning it hailed from outside the solar system and was not gravitationally bound to the sun. Observers quickly noted unusual traits: a composition richer in carbon dioxide than many familiar comets, an asymmetric dust plume geometry, and an orbital inclination only slightly offset from the ecliptic. Those signs suggested a stranger origin and a structure that might not respond to solar heating the way typical solar system comets do. Then, as it plunged inward and faced the sun's intensifying heat, the unexpected happened. A catastrophic disruption, not a gentle shedding. The object fractured violently, releasing energy, vapor, and solid fragments that fanned outward in a chaotic pattern. The mechanics of that rupture deserve careful attention. A body traveling through interstellar space for eons accumulates a history of micro-impacts, radiation damage, and thermal processing very different from objects born inside a planetary disk. As 3I/ATLAS approached perihelion, the increasing solar flux caused volatiles to sublimate, generating internal gas pressure. At the same time, differential heating, possible pre-existing weaknesses, and rotational stresses could have combined to produce mechanical failure. The breakup was not merely an incremental evaporation of surface ice, it was a structural collapse that released large pieces into independent trajectories. In vacuum, such fragments retain the parent's momentum, but also add relative velocities from the explosion itself, creating a dispersed cloud whose subsequent motion is sculpted by gravity, radiation pressure, and other subtle forces. That debris cloud is far from uniform. Within it are particles that range from fine dust to pebble and boulder-sized chunks. Small grains are susceptible to solar radiation pressure and electromagnetic interactions, so their paths can be deflected significantly relative to heavier fragments. Larger pieces, by contrast, preserve more of the original inertial vector and follow more predictable orbits. This size heterogeneity translates into a spectrum of consequences. Microscopic particles can harm spacecraft surfaces and optics. Meter-scale fragments could, in worst-case scenarios, survive atmospheric entry and make ground impacts. Because the explosion produced a spread of velocities and directions, each fragment must be tracked independently to assess its evolution and potential intersection with Earth. Why does any of this matter beyond dramatic headlines? We have witnessed interstellar visitors before. 1I/Oumuamua and 2I/Borisov passed largely unperturbed through our neighborhood, but those objects did not fragment inside the inner solar system and send material toward our planet. 3I/ATLAS did. That single difference turns an observational curiosity into an unprecedented opportunity and a new class of challenge. On one hand, fragments from an interstellar object carry with them the chemistry and physical record of a distant stellar nursery. On the other, unpredictably dispersed fragments complicate planetary defense and risk assessment because they multiply the number of possible intercepts and reduce lead time for intervention. Practically speaking, the immediate hours and days after the breakup were a scramble. Telescopes across the globe pivoted to observe the event. Radar operators tuned their arrays to ping larger fragments, and spectrographs recorded fleeting signatures of vaporized material. Each new positional measurement refines orbital solutions. Each spectrum narrows compositional hypotheses. Agencies such as NASA's Planetary Defense Coordination Office, the European Space Agency, national astronomical centers, and independent observatories rapidly coordinated data sharing and modeling efforts. The collaboration was necessary. An expanding cloud of fragments cannot be tracked by a single facility, and international coverage ensures continuous observation as the Earth rotates. Importantly, NASA's confirmation that debris is inbound should not be conflated with a guaranteed catastrophic impact. The vast majority of fragments are expected to be tiny and to disintegrate harmlessly in the upper atmosphere, producing meteor streaks or diffuse noctilucent glows. Our atmosphere does an excellent job of protecting the surface from much of the solar system's litter. Yet the devil is in the distribution. The number of fragments, their size distribution, density, relative velocities, and precise orbital intersections determine the real-world effects. A stream of microscopic particles might erode satellite surfaces and degrade sensitive optics. A small number of larger fragments, though unlikely, could produce localized impacts if they survive entry. This situation underscores a broader point. Planetary defense planning must consider not only asteroids and comets formed in our own system, but also visitors from interstellar space. Interstellar objects can arrive with high velocities and minimal warning. When they fragment, the challenge multiplies because tracking many small bodies is inherently more complex than tracking a single large one. The 3I/ATLAS event highlights the need to expand our hazard calculus to include fragmentation scenarios, rapid follow-up observation networks, and adaptive modeling frameworks capable of ingesting continuous streams of positional data. From a scientific perspective, the event is extraordinarily rich. Each fragment is a potential sample of matter formed in a distant system, a rock or grain that may contain isotopic ratios, mineral phases, and organic compounds unlike those typical of the solar system. Isotopic analyses of oxygen, nitrogen, or other elements could reveal differences in nucleosynthetic histories and local chemical conditions where the fragments formed. Spectroscopy of ablation trails reveals elemental lines in real time as material vaporizes high in the atmosphere. If fragments survive to the ground, laboratory studies using mass spectrometry, electron microscopy, and nano-SIMS could probe structural and compositional features at micron and submicron scales. A recovered fragment from 3I/ATLAS would be the first physical piece of an extrasolar object available for hands-on study, a treasure trove for cosmochemistry. There are also compelling implications for theories of interstellar material exchange. If objects like 3I/ATLAS are common and prone to fragmentation near stars, then the exchange of dust and organics between systems may be an underappreciated mechanism for distributing prebiotic material across the galaxy. While the discovery of complex organic molecules in such fragments does not equate to a discovery of life, it bears directly on the prevalence of life's chemical building blocks beyond the solar system. Studying the organic inventory of interstellar fragments helps answer whether the chemistry that seeded Earth is a local fluke or part of a widespread galactic pattern. Operationally, the event has immediate consequences for spacecraft safety. Satellites in low Earth orbit and beyond operate in an environment now temporarily enriched with high-velocity particles. Although the risk of catastrophic satellite loss from a single fragment is small, cumulative exposure can degrade solar panels, contaminate optical instruments, and increase the chance of micrometeoroid penetration in thin shielding. Satellite operators are evaluating minor orbital adjustments for key assets, implementing protective modes for vulnerable instruments, and running collision risk assessments. Deep space probes, especially those traversing orbits near the debris path, face different sets of trade-offs and may require more targeted mitigation planning. Modeling the post-breakup dynamics of the debris is a technically intense task. Classical Keplerian trajectories provide a baseline, but refined models must incorporate radiation pressure that dependent on fragment area-to-mass ratios, interactions with the solar wind that can produce charged particle forces on dusty plasma, and even subtle thermal forces for irregularly shaped fragments. Numerical simulations run on high-performance computers ingest observational updates and produce probabilistic maps of future positions. Those maps inform when Earth is likely to intersect denser portions of the stream and which regions of the atmosphere or surface might be touched by surviving fragments. Meteor scientists are already producing shower forecasts. If the debris density and geometry produce a sufficiently thick column where Earth's orbit crosses, observers could witness a transient meteor shower, unlike any tied to a known periodic parent. The expected visual display would depend on particle concentration, size distribution, and entry velocities. Amateur astronomers and wide-field camera networks are preparing to record and timestamp any meteors that appear, because triangulated observations are essential to reconstruct fragment trajectories and potential recovery zones. Recovery efforts, should they be warranted, are complex operations. Terrestrial searches rely on triangulating luminous entry paths, combining radar detections and eyewitness reports to define strewn fields where larger fragments might land. For ocean falls, ships with magnetometers and sonar are needed, coordinated with aircraft for surface and aerial reconnaissance. Once fragments are located, they must be handled under strict quarantine and contamination control to preserve extraterrestrial signatures. Cleanroom protocols, similar to those used in curated meteorite research and planetary sample handling, will be necessary to avoid introducing terrestrial contaminants that could obscure subtle isotopic or organic signals. Those practicalities dovetail with legal and policy questions. Current international space law and treaties provide broad principles for activities in space, but are not finely prescriptive about ownership of extraterrestrial material that falls to Earth. Science communities and policymakers will likely need to negotiate principles for equitable access, sample sharing, and research priorities, ensuring that discoveries are broadly analyzed and that data and samples are available to the international research community in ways that maximize scientific return while respecting sovereign jurisdictions. Beyond the immediate technical and legal dimensions, the 3I/ATLAS event is a catalyst for new mission concepts. Engineers and mission designers have begun discussing rapid response smallsat swarms or piggyback missions that could, under favorable circumstances, intercept dispersion streams and sample material in situ. Such missions face significant challenges. Fast intercepts require high delta-V and rapid decision-making, but the notion of flying sampling platforms into a newly formed debris stream is no longer pure science fiction. Even remote in-situ observations with dust collectors and spectrometers on agile spacecraft could yield data unattainable from Earth alone. Theoretical science will also benefit. The fragmentation mechanics of 3I/ATLAS provide a natural experiment into the structural integrity of interstellar bodies. Was the breakup driven primarily by thermal stresses, rotational spin-up, volatile-driven outgassing, or a combination of these? Detailed mapping of fragment velocity vectors, sizes, and directions offers clues to the parent body's internal layering and strength. In essence, the explosion is an autopsy from which researchers can reconstruct the object's interior and formation history, refining models that predict whether interstellar objects tend to be robust or flaky when they encounter stellar environments. Public communication and outreach are critical in moments like this. Scientists must strike a balance, convey the profound scientific opportunity without amplifying fear. Transparent briefings, clear explanations of uncertainties, and accessible guides to what to watch for in the skies help maintain public trust. Planetariums, observatories, and educational institutions are stepping up with live feeds, data visualizations, and curricula that bring students into the discovery process. Citizen science platforms enable enthusiasts to contribute observations that complement professional datasets, democratizing the response and enriching the global record. The cultural resonance of an interstellar object exploding near our star is also noteworthy. The idea that shards of a rock born around another star might streak through our sky or land on our planet is an evocative image. It presses home the reality that the galaxy is not merely a distant backdrop, but a dynamic environment capable of moving material between systems. Poets, filmmakers, and artists will almost certainly incorporate this episode into new works that reflect human curiosity, vulnerability, and the deep connections binding worlds across light years. At the same time, this event sharpens scientific debates about panspermia and material exchange. Confirming complex organic chemistry within incoming fragments would strengthen the case that prebiotic molecules are widespread and transferable across interstellar distances. That would not prove life outside Earth, but it would illuminate pathways by which the raw ingredients for life can travel between stellar nurseries and planetary systems. The implications for the ubiquity of life's building blocks are profound. In the technical heart of the response, new tools and collaborations are emerging. Adaptive orbital solvers use machine learning to rapidly assimilate observational updates and produce refined impact probabilities. Global arrays of wide-field cameras and all-sky spectrographs are being coordinated to maximize temporal and spatial coverage, and laboratory networks are ready to receive, quarantine, and analyze any recovered material. The event is driving investment in capabilities that will outlast the immediate crisis and strengthen humanity's preparedness for future, perhaps larger, cosmic encounters. Looking forward, the months and years after this breakup will bring layered returns. If fragments produce meteor activity, the sky will offer ephemeral spectacles and priceless spectroscopic data. If meteorites are recovered, laboratories may study them for decades with ever-improving techniques. In policy terms, the episode will likely accelerate efforts to strengthen global observation networks, refine contingency protocols for fragmented objects, and formalize cooperative frameworks for sample access and analysis. At a cosmic scale, the Sun played a crucial dual role. By lighting 3I/ATLAS and subjecting it to rapid heating, our star acted as both illuminator and trigger. It revealed the visitor's nature and set in motion the physical processes that scattered its remains. That interplay of radiation, gravity, and material fragility produced a chain of events that now unfolds across the inner solar system and in our skies. Scientists will study not only the fragments themselves, but also the dynamical choreography that carried them from a distant origin into near-Earth space. We are witnessing an extraordinary confluence, the death of an interstellar traveler and the birth of a new field of inquiry centered on fragments from outside our system. The debris headed our way is not merely potential hazard, it is also messenger, sample, and story. Each grain and shard carries the record of formation in an alien environment, then a lengthy voyage through the cold and empty spaces between stars, and finally a violent end in the warmth of our star's embrace. For scientists, policymakers, and the public alike, the event crystallizes the reality that the galaxy remains a place of active exchange and surprise. As telescopes gather more data, as radars ping larger fragments and spectrographs catch fleeting atomic signatures, and as laboratories ready themselves for possible recoveries, the narrative of 3I/ATLAS will continue to evolve. New models will refine our expectations, recovery teams will prepare for practical contingencies, and the public will have a front-row seat to one of the most singular astronomical stories of our time. Whether the legacy of this event is a dazzling meteor display, a handful of recovered extrasolar rocks, or a trove of spectroscopic evidence, the scientific and cultural harvest will be profound. The story of 3I/ATLAS is not finished. Each night that passes brings more observations, more refinements, and more clarity about what portions of the debris will meet the atmosphere and what will arc harmlessly past. For now, the world watches as a cloud of fragments from a remote birthplace threads its way through our celestial neighborhood, offering both a reminder of our vulnerability and a rare chance to expand humanity's knowledge about the composition and dynamics of material that travels between the stars. Curiosity and caution walk together as the scientific community reads the messages carried by these tiny ancient messengers. Beyond the telescopes and technical briefings, the human side of the 3I/ATLAS story continues to unfold with quiet intensity. Teams of researchers work around the clock, not to stoke panic, but to transform raw observations into reliable models and actionable insight. That tempo matters. Real-time positional updates, spectral snapshots, and radar pings arrive continuously, and integrating them quickly refines predictions about which fragments might intersect the atmosphere and which will drift harmlessly past. One practical consequence has been a renewed emphasis on observational agility. Large survey instruments provide vital depth and sky coverage, but responsive smaller telescopes, mobile radar units, and distributed camera arrays have proven invaluable for tracking rapidly evolving fragments. These nimble assets fill observational gaps, deliver dense time series data, and enable continuous follow-up when a fragment's brightness or trajectory changes unexpectedly. The voice of amateur astronomy has been prominent and constructive. Skilled backyard observers and independent networks contribute time-stamped astrometry and meteor reports that professional facilities cannot always obtain on short notice. Organized citizen science platforms are channeling that effort, assigning volunteers to monitor sky sectors, log meteor streaks, and submit calibrated brightness measurements. That collective participation expands coverage and makes the global response more robust. Ethical and logistical questions about recovered material have also surfaced. If a fragment is located on private property, who safeguards it? How should governments and museums prioritize access while preserving scientific chain of custody and avoiding commercial exploitation? Existing meteorite handling protocols offer a starting point, but the extraterrestrial origin of these fragments and their potential astrobiological novelty argues for tightened quarantine, transparent reporting channels, and agreed methods for rapid but careful transfer to accredited laboratories. The educational and outreach opportunities are enormous. As fragments or luminous traces appear in our skies, educators can use them to illustrate orbital mechanics, spectroscopy, and the scientific method. Live feeds from observatories, interactive data portals, and classroom datasets let students handle real astrometric measurements, test hypotheses, and watch models evolve. For many learners, participating in data collection or analysis turns abstract physics into tangible discovery and inspires the next generation of scientists. Operationally, the event has accelerated interest in rapid response missions. Concepts once relegated to speculation are getting serious attention. Small, agile collectors with aerogel capture panels, deployable sensor swarms that can sample dust in situ, and prepositioned small sats held in parking orbits ready for rapid launch. Each idea faces engineering hurdles, high delta-V, precise timing, and rapid mission authorization. But even limited in situ sampling could yield data impossible to obtain from Earthbound observations alone. The psychological dimensions of the event also deserve attention. Cosmic incidents can trigger public anxiety as readily as fascination. Clear, measured communication is essential. Authorities should explain probabilities, outline monitoring efforts, and offer tangible guidance about what citizens might actually observe. Community engagement events, expert Q&A sessions, and transparent data releases help build trust and prevent rumor from outpacing evidence. Scientifically, the sequence of approach, heating, fragmentation, and dispersion forms a single, comprehensive experiment. Thermal physics governs early volatile loss. Fracture mechanics dictate how and when brittle failure occurs. Radiation pressure and solar wind sculpt fragment trajectories. And atmospheric physics governs ablation and deposition. Studying all these phases together provides insights into material strength, volatile inventory, and the response of alien bodies to stellar environments. The broader astrophysical consequences are profound. If fragile interstellar travelers are common, stellar systems may routinely exchange dust and complex organics. Such transfer would not prove panspermia, but it would suggest that many systems share similar raw chemical ingredients. Determining isotopic ratios and organic inventories in recovered material would clarify whether prebiotic chemistry is a galactic commonplace or a rare fluke. From a technical perspective, the event is driving advancements in modeling non-gravitational forces. Where once such forces were secondary, they are now central to accurate short-term predictions. Improved algorithms for solar radiation pressure, plasma interactions, and thermal recoil effects are being developed and validated against the incoming stream. These models will strengthen tracking for future transient events and improve the fidelity of debris forecasts for satellites and ground impacts. In the near term, observers may witness transient meteor displays, sporadic bolides, or only subtle increases in micrometeoroid flux. Outcomes depend on the stream's fine-scale structure and density. Regardless of spectacle, the scientific harvest will come from data, emission line spectra of ablating fragments, radar cross-sections that constrain size and shape, and any recovered samples whose isotopic and mineralogical signatures can be interrogated in laboratories around the world. International policy conversations are also evolving. The event highlights gaps in legal frameworks governing extraterrestrial material and suggests a need for agreed-upon protocols for reporting, recovery, and sample sharing. Multinational agreements that preserve open scientific access while respecting sovereign jurisdiction would maximize collaborative analysis and ensure that discoveries benefit the global community. Ultimately, the 3I/ATLAS episode is a story of preparedness meeting opportunity. It tests global observation networks, exposes shortcomings, and catalyzes investment in capabilities that will outlast this single event. Whether the legacy is a memorable meteor display, a handful of recovered extrasolar rocks, or a new generation of modeling tools and rapid response missions, the outcome will be a lasting expansion of humanity's capacity to understand and respond to the wandering matter of the galaxy. As the debris continues its silent passage, scientists, citizens, and policymakers watch closely. Every recorded flash and every spectrograph line is a clue. Every recovered grain a chapter in a story that began around another star. The coming weeks and months will refine probabilities, map strewn fields, and perhaps put tangible pieces of another system into human hands. That prospect turns abstract cosmic processes into an immediate shared enterprise of discovery and stewardship. Now is the time for global cooperation and open science. Shared observations, common protocols for recovery, and public communication will maximize discovery and reduce confusion. Whether fragments arrive as harmless meteors or yield recoverable samples, the scientific and cultural value will be greatest if nations work together. 3. I/ATLAS challenges us to respond collectively, combining curiosity with responsible stewardship of our fragile planet and sustained funding support.